Okay, so now we're going to introduce Lemma 1. Okay, so Lemma 1 says where V is a vector space, S is a subset of V, the vector space V, and the vector V is an element of V, then these two sets, the set of the union of S and excuse me, let me repeat that. Let me start over. The spanning set of the union of set S and the vector V, the singleton set with vector V, is equal to the spanning set of S. Okay? So again, let me repeat that. Where V is a vector space and S is a subset of V, so S is a subset of V, and V is a vector, is an element of the vector space, then if we take the union of the set, the subset, and that vector and take the spanning set of that, that will equal the spanning set of S if and only if V is also in the spanning set of S. Okay? Now it's if and only if, which means it's bidirectional, so it's biconditional. Okay? So now one way is easy, okay? So in fact, the one way we're going to show this, so we have to show it's true both ways. In order to show that these two are equal, we're going to have to show that it's if and only if, right? So we can go this way, right? And then we'll have to show it the other way. Now going this way is easy because we can actually use the proof by contrapositivity. We could use that, and it's actually kind of cool because 1/2, in other words, going this direction, is immediate when we use contrapositivity. Because if, excuse me, if V is not an element of the span of S, then the sets are not equal, right? And why is it not equal? Well, easy, because vector is in the spanning set of the union of S and the vector V. So they can't be equal, right? Because we already know it's in here. Okay, because what is it? We're taking all of the linear combinations of this, the union of this set and this set. So vector V has to be in there. Okay, so by contrapositivity, if the vector is not in this spanning set, then the sets cannot be equal because we know it's in this set. Okay, so that's one way. Okay, so now, what about the other half of the proof? Let's assume the vector V is an element in the span of S. so that, right, vector v is equal to c1 s1 plus all the way to cn sn, right? Oh, you're forgetting. These are all vectors. For some scalars c sub I and vectors s sub I in S. Now, we're going to use mutual containment to show that the sets are equal, right? So we're going to use mutual containment to show that this set and this set are equal. What does that mean? It means that we're going to show that every element in this set is also an element in this set and vice versa. Okay. So now, this containment is self-evident. Which way do I want to go? Yeah, so if we start with this, S, U, okay, so we take the span of that set. Okay. Okay, so now it's clear, right? So again, oops. So we're assuming, right? We're assume vectors in the spanning of S, right? Such that the vector v can be written as a linear combination of vectors in S, right? And so showing the self-containment this way is clear, right? Because if this is in the spanning set of S, then it's also going to be in the spanning set of S union the single, oops, I'm sorry, gotta have the bracket of those two sets. Okay, so that's clear. Okay, now, to show the containment the other direction, let's let a vector W be an element, right? To show the other way, let's let W be an element of the span of S union V. Then the vector W is a linear combination of the elements of that set, right? The union of those, right? So that means W can be written as a linear combination of S union V. Okay, so now, here's how we'll do this. We'll do S, we'll say it's C1, S1, plus dot dot dot, plus C sub K, S sub K, plus we can go to or no, I'm sorry, hold on a second. Oh, we already got 1 through N here. Let's not use that because, yeah, let's not use that. Let's use N, oh, N plus 1. Yeah, we want to start with N plus 1. And then let's use N plus K, N plus K. And then what we'll do is we'll do C sub N plus K plus 1 times the vector V. Yeah, that'll work. So all I did was I used linear combination of C's, where the C sub i's are real numbers, and S sub i's. Now, one thing to mention, some of these S sub i's here may be the same as the ones in V. And that's okay. It's not going to matter, because we can just simplify things by adding like terms. So that's not a big deal. So now if we expand this out, let's expand this out. So we get W equals C sub N plus 1, S sub N plus 1, plus dot dot dot, plus C sub N plus K times S sub N plus K. Now we're going to do plus C sub N plus K plus 1 times the quantity. Now we're going to substitute in for V, which is C1 V1 plus, well, I won't write that out. C sub N, S sub N, like so. Now, we recognize the right-hand side of this as a linear combination of linear combinations of the vectors in S. Right? So again, the linear combination lemma comes into play because we just showed that this is just a linear combination of linear combinations. And thus, by the previous lemma, it is in the spanning set of S. And we're done. And so therefore we just showed that the two sets are equal. Awesome. Have a good day.